Swayam Prabha. Digital India. Educated India.
Welcome back. So, we were discussing calculation of force from the principle of the change of the magnetic field energy. Today, I am also going to introduce to you a new concept called co-energy, and again derive how to calculate the force from the rate of change of co-energy with respect to the x variable. Both the methods are going to be equivalent. After all, in a physical system, when something is happening, the force which is being calculated is force which will come out to be the same thing, whether you take a energy principle or a co-energy principle. As the co-word indicates, it is very closely related to the energy principle, but it improves your convenience, because if you recall what I had talked yesterday, while calculating the force, we had to assume that and taking the partial derivative of magnetic field energy with respect to x with a minus sign, we had to assume that lambda remains constant, but in many circuits actually it will find that current remaining constant is a much easier thing to do. So, what we are trying to do today is to move away from the state variables lambda and x, the flux linkage lambda and x, to something which is I and x, and in a linear system, of course, probably 1 and 2 are, you may not see much difference in ease or convenience, but probably in a non-linear system, I think the many places the co-energy concept turns out to be much more beneficial. The results will be the same whether you apply energy principle or you apply co-energy principle to calculate the force or the torque. The results are going to be the same. The only thing is you do some extra homework earlier, do some massaging on the variable state function and this and that, and get it into another form which looks much more convenient to you, and where the applications become much more easier later on while you are using the concept. The underlying physics is essentially the same. To do that, to dive deep into this, I think it will be better, because we are going to carry forward the same example and also develop from the theory, from transition from energy to co-energy. So, I think we will do a quick recap of what we did in the last lecture. Usually I do not run this recap because you have a recorded lecture already available, you yourself can do the recap, but in this particular case I think doing it here and now is going to be a useful thing to do. So, we had this relay kind of a structure set up last time, and if you recall, this is what was there, and we had a armature. This is my armature which is there, or a plunger or whatever, and when I energize this magnetic circuit, this will be pulled, because magnetic field will attract, you have seen this right from your school days. Iron filings are attracted by a magnet. The same principle is going to be used here, and as you do that, our job is to calculate what is the force which is going to be produced. So, we said that basically our initially the system is unenergized. This whole action is happening because I am pushing electrical energy into this system, and the work, this exerts a force of FLD on this mechanical source, it exerts, and if it exerts and there is a movement of dx in this direction, then the work done will be FLD dx. Because actually the force is other way around, we will see that it comes with a minus sign and all that, that's a subsequent part of it. But the energy that you put in and the work that gets done, the difference of that is what is the increase or change in the stored energy in the magnetic system. So, this is our fundamental principle. So, the how much energy do you pump in? This whatever is the EMF countered here, E times I times dt, E into I is the power times dt is the incremental electrical energy which is pushed in, and for E by Faraday's law and our sign convention appropriately set, this is set to d lambda by dt. So, you get I d lambda. Now, the mechanical work done is force which is a function of FLD called the field times the dx, this is the incremental work which is done, and the energy, electrical energy, this is what is exactly called a motor action, is equal to change in the magnetic field energy plus the change in the mechanical energy. So, therefore, electrical energy which is pumped in I d lambda is same as the change in the magnetic field energy plus FLD dx. This equation I am going to need later on. So, I will keep it for my future use. Now, we will need this. So, keep a track of this equation. Now, since I am in a recap mode, let us look at this very important last lecture that we did. This change in the field energy is the difference of the energy which is electrical energy inputted minus the mechanical energy work done. And if you want to, if you are starting on this lambda x plane, there are two variables here, the flux linkage lambda which is n times of phi, and the x variable which is there. And if you if in these are taken as the two state variables, why are these two state variables? Because of this equation, this very fundamental equation, it comes in terms of d lambda, it comes in terms of dx, and lambda is only lambda is related to current and dx. So, these are two independent two independent state variables of my system. Any one of them I take away, I will not be able to describe or work through this system, and hence but I cannot have lambda and I simultaneously. I cannot have three state variables. I cannot have lambda, I and x as state variables. Among lambda and I can choose only one. So, in this lecture I am also going, when I am going to introduce you the concept of Poe energy, I am going to replace lambda by I and then show you what's the new magic that you will see. But two state variables are bare minimum required here. And now, let us say that this is our lambda x final position, that means at the final position we are going to set using this voltage source, lambda can be controlled from there, we are going to set up this lambda, and of course, x we want to bring it up to some point x naught. So, that is where we are going to stop. So, we want to move to this place initially, because we are let us say having the there is a switch here and we have not closed the switch. So, therefore, initially our point is this, and we reach finally point here. We may take a trajectory which looks like this, that means as my lambda increases and the x is also increasing, this is maybe the trajectory that I take. Now, because I am taking this as a lossless system, and even this is taken as a massless magnetic armature. So, basically whatever is the whichever way this is a conservative field, as we say it, because there is no kind of there is absolutely no loss of any kind which is happening in here. So, the energies are going to magnetic field energy which is stored here, and it here is 0, whatever it is here, this is going to be independent of the path I take. So, though actually I may have gone through this, the actual machine may have gone through this path, for the sake of calculation I can take any other path which comes back to this. You could even take like this and come back. Even then your calculations are not going to be different. This is what is meant by integral which is path independent, which corresponds to conservative fields, where the energies only depend upon the initial state and the final state and are independent of the path through which we went. So, to calculate what is the magnetic field energy here, what was suggested in the last lecture was that first move along this part 2a and then move along the part 2b, you are again reaching the same point, but the advantage of moving along the part 2a is that one is that along the part 2a, one is that the d lambda is 0. In fact, here the whole lambda itself is 0, the d not only anywhere else horizontal line if you draw, lambda is constant, so d lambda is 0, but this horizontal line has another advantage, that lambda is also 0. So, when you move from here, that means there is no current, there is no, this source is temporarily disconnected, the whole system is unenergized, and so there are no attraction or attractive forces or anything which is going on here. So, for example, if it is closed initially and you want to move it up to this, you can just move it to whatever position you want to move it. Why? Because there is nothing, it is an unenergized system. So, not only d lambda is 0, but even no electromechanical force is also there. So, FLD is also 0, f of FLD is also 0, and therefore, FLD dx is also 0, and because FLD dx is also 0. So, along this path when you move from here to here, now to calculate the energy, magnetic field energy at the final point, I am doing an integral on this moving from, and then taking a path from 2a to 2a, and then the path to 2b. So, what happens is what happens is along the path 2a, dFLD turns out to be 0. So, if I want to calculate what is the magnetic field energy at my final position where the flux is lambda naught and the state variable is x naught, I have to reach there first from 0 starting point, take a part 2a, reach here which is lambda 0, sorry x, this is the point which I have to reach, and then from here I have to reach to this particular point. So, when I do this integration along split this integral is to be done along the part 2, which is sum of part 2a plus the sum of integral of part 2b. Now, the integral on the part 2a turns out to be 0, unenergized system, you just separate it out a bit, no work is required to be done. So, therefore, not surprising that this is 0. So, everything that gets done as if you first moved to find, as far as how much a magnetic field energy is set up, as if you moved it up to here and then started increasing the current in the coil and holding it there, not allowing it to move, holding it there. That is why a mechanical source is also shown here, and then reaching x naught is already there, only the lambda has to change to lambda naught. So, when the x is not changing and if we have taken this to be a ideal ferromagnetic material mu r equal to infinity, then this will look like a linear system in the path 2b. So, on the part 2b, because x is not changing, dx is 0, and therefore, because the dx becomes 0, so dw field becomes equal to I d lambda, and therefore, dw field becomes I d lambda, and this lambda has to be increased from 0 to lambda naught. So, I get I d lambda by d lambda. Now, very carefully notice that this integration state variable is lambda. This is not this is in terms of current. This has a relationship with lambda. How, on what is the relationship? Lambda is equal to inductance at that point x naught times the current which is there. So, therefore, to do the integration with respect to lambda, I replace current by lambda by L x naught times of d lambda, and then when I do the integration, this L x naught is constant. Once the x naught is fixed, L x naught is constant, and therefore, what do I get? I get this integral as half of lambda square by L x naught, but again I can instead write lambda naught as L x naught times of I naught in this case, and therefore, I get half of L x naught I naught square joules. So, this is the magnetic field energy which is set up. Now, we carefully saw how it is set up. This is very important because we are going to deal with systems in which there are moving structures or parts, and therefore, this aspect had to be handled carefully. Now, the same magnetic field energy, our physics tells us that the same magnetic field energy can also be written as this being the dot product, you can write it b dot h dot b cos of theta. So, this is the volume density, and therefore, it could be calculated like this, and h can be written because we are talking in terms of lambda, means our state variable is in terms of b. So, because our state variable is terms of b, so therefore, I can write h is equal to b by mu, and instead write this volume integral w f l d as volume integral v over half of b square by mu d v. So, now we have taken care of how the magnetic field energy is set up. Then we did this example, and this example is again going to be needed in the today's class also. So, we need to again have a look at it. What we have is a magnetic structure, a plunger which you can pull it in by exciting the sending the current here. So, it is a you can use to do your work here, mechanical work you can do. So, it could be a heavy weight sitting here, and then you excite current, and then it pulls in. The electricity input goes from here, and the mechanical work gets done here through the electromechanical interaction which is happening in this air gap, the magnetic field being set up. First thing, let us find out what will be the magnetic field energy as a function of x. So, therefore, we said that field energy is half of L x I square, again a linear kind of a system here, because I am taking this to be infinity. So, only thing being the MMF is basically just expended in the air gap which has a constant b. So, therefore, it represents a linear system, and the magnetic field energy we just derived it is as half of L of x I square. Now, we also know that inductance can be written as square of the number of turns divided by reluctance, and to calculate reluctance, this is the MMF. There is nothing, iron being ideal mu r infinity, its reluctance is 0. So, one reluctance for the first air gap, then a 0 line, then another reluctance for the next air gap which is symmetric or identical, and then close it. So, therefore, the reluctance is just the summation of the reluctance of 2. In other words, you can just imagine that this G plus this G is added, the net air gap is 2 G, and the this it is x distance away. So, this overlap distance is d minus x and the depth is L. So, the area of cross section which is seen by the flux, if the flux is going like this is the area of cross section which is there, d minus x times of L. This is what we are seeing is the reluctance, and I substitute it there in n square reluctance here. I get this taking d out as a common factor. So, d minus x can be written as d into 1 minus x by d. This is what I did, and because it is a reciprocal thing. So, this goes up, this goes down, and I get substitute it here, and I get magnetic field energy now as a function of I, but I get magnetic field energy as a function of I. Now, we took some values that let us say the current is this, the air gap is this, the number of turns is this, the distance and the L is so and so, and we got WFLD as just a function of f, the magnetic, because the current has been current has been held constant. So, because the current has been held constant, the magnetic field energy now only changes according to the x, and it is actually like not connecting a current source here, which is a controlled current source. It requires something extra to be done to keep the current constant, unlike a voltage sources which are naturally available in like a battery or something which are naturally available. Current sources are not naturally available. If you want to create that gadget, it has to be a controlled system. More about that later. Anyway, so because you are connecting it with a constant current source, the field energy WFLD turns out to be so many units being joule. Then we came to the concept of calculating the magnetic force. And how did we go about calculating the magnetic force? We are going to again repeat some of this here. See, with this one we already saw the incremental change, infinitesimally small change in the magnetic field energy, which is a function of state variable lambda and x, which today we will replace again by state variable I and x, is given by, and that is what we have to see, is given by incremental electrical energy pushed in minus the mechanical work which got done out of it is the incremental change in the magnetic field energy that happens. Now, this we can, using partial derivatives and knowing that there are two state variables lambda and x, we can write this increments infinitesimally small change in can be written as partial derivative with respect to lambda into d lambda plus partial derivative of the magnetic field energy with respect to x times of dx, and then the left hand side is the same, right hand side is the same. The state variables are two independent quantities. So, when we equate this equal to this has to match with this has to match with this. Because of this, we get I to be equal to the the partial derivative of the magnetic field energy with respect to lambda, which means here when I say partial derivative of magnetic field energy with respect to lambda, by that I mean that here x will be held constant. This is while doing the analytical computation, and then FLD turns out to be minus of partial derivative of the magnetic field energy with respect to x, which means here the lambda will be held constant, not I, lambda will be held constant. That is what is important. And why? Because it is a moving system. So, the L keeps changing. So, when I say lambda is the held constant, if something moves and L changes, even then lambda will be held constant, means I will have to be changed. So, this is not like everything fixed, only one fixed air gap. So, the lambda equal to L is a constant. If L is a constant, really speaking, it is very straightforward. You can call lambda as a state variable or I as a state variable, they are just scaled multiples of each other. But here, even though lambda is still by definition L equal to I, L is also a function of position, and the position is changing. So, whether I say lambda is constant or whether I say I is constant are two different things. This one thing I want to get it very straight through you, you know, that when L is a function of x and lambda is equal to L is a function of x times of I, because I have not taken non-linearity of the BH curve. When I say I remaining constant, as x changes lambda will change. If I say lambda remaining constant, as x changes I will change. So, that is why I cannot take both of them simultaneously as my state variable, they require different treatment. Anyway, so we came to this conclusion that the force created due to the interaction of the magnetic field is minus of rate of change of magnetic field with respect to partial derivative with respect to x. Now, we want to apply this on this particular example where we have already calculated this. So, what did we do? We said that we know magnetic field energy is so and so. We can write this as in terms of lambda and L like this, because lambda is our state variable. So, the W should be expressed in terms of lambda, but in doing so that which was sitting on the numerator L has now moved to the denominator. When I do the co-energy thing, you will see that actually I will not change this. So, the L which is a function of x there is sitting in the numerator, but in the co-energy discussion that I am going to do a bit later on, but here it has moved to denominator. So, FLD which is minus of rate of this, when I substitute it here and I do this I take it here and I do partial derivative with respect to x, it is 1 by L square into del L by del x, which we substituted, and this part is just mechanical. So, I am not repeating this, turns out to be minus n square mu 0 L by 4 g I square. Now, the same thing today we will try to get from the co-energy principle also. That is our job, that we want to get the same thing again from co-energy principle. So, let us come to see, try to understand now what we mean by the co-energy. It is actually one word, it is not actually two words. So, let me not write it as two words. What is one word should not be split as two words. If you write it probably in your Microsoft Word or anything like that, it may not show you as this, and then it may suggest you to do this, but please do not do it. Co-energy is only one single word. Now, let us keep this equation handy. I had said that this equation is our building block. I d lambda, in other words WFLD, which is a function of lambda and x is I d lambda minus FLD dx. This is what we had said earlier. Now, let us say let us define co-energy as I times of lambda. I will use dash as a notation for co-energy, W dash FLD. Dash is to say it is just co-energy, this is something very similar kind of thing, but it is going to be in terms of state variable. Instead of lambda, change of state variable is being done. Because the change of state variable is being done, another state function, magnetic energy in terms of lambda and x was one state function. Now the state I and x are going to be my state variables. So I am going to, for that convenience sake, I am going to define magnetic field co-energy as another state function, which is lambda times of I or I times of lambda, whichever way you want to call it, I times of lambda minus W FLD of, but this is in terms of lambda times of x. So, this is the relationship between between energy and co-energy. Now, let us look at, if you, I will geometrically explain it very soon, but let me just do a bit of algebra first. If I look at dWFLD dash incremental change, then I have to apply the d operator on the right hand side also, like this, but this can be written as I d lambda plus lambda d I minus dWFLD lambda times of x, or just let me rearrange it, lambda d I plus I d lambda minus dWFLD of lambda times of x. Now, can you see from here, I d lambda minus dWFLD. So, that means this one should go on this side and this one will come back on this side, and then I will get this expression. So, therefore, I will get this as lambda d I plus FLD plus of, this is 2 times f is repeated and I get confused mentally about it. So, this the rate incremental change in co-energy is going to be given by something like this. But again, following the similar principles that we discussed earlier, and now I is and x are the state variables. So, I can write this as this partial derivative with respect to I times of d I plus partial derivative of co-energy with respect to x times of dx, and let us call this as 1, let us call this as 2. Then if you equate 1 and 2 state variable to state variable, right. If you do this, equate 1 and 2 state variable to state variable, then what will you get? You will get lambda to be equal to partial derivative of this times of I. Usually we are not using this, we are more interested in the other equation which is related to computation of the force or torque or things like that. So, the F of FLD, force of associated with the magnetic field, is given as positive rate of change of co-energy. Positive means coming with a plus sign, here it is coming with a plus sign. When we were doing it with respect to magnetic field energy, this was coming with minus sign when this was not there. So, positive sign of this, in a sense you can see that this got accounted in our definition here. These two come with, when one increases other decreases given a certain product I lambda. So, you get this rate of partial change of partial derivative with respect to x. So, what we are saying is this force is also the rate of change of co-energy instead of energy with respect to the state variable state variable x. Okay. So, if you now want to apply this, if a let us now look at geometrical interpretation of this first of all. Let us, by doing the geometrical interpretation, I am going to take a more general case of a nonlinear kind of a system. So, I have something like this, where this is the plane is my lambda and this is the I. As the current is increasing, because the magnetic element is tends to saturate. So, my this is has some kind of a nonlinear relationship. Let us say that I am at position A and think of this example here that we discussed here. Think of this example. As this plunger moves inside and inside, the magnetic you will have more iron. So, for the same current, higher flux will be set up. So, let us imagine that this is the, when I move the plunger is pulled inside a bit, for the same current, because I have more iron paths here. So, my lambda I for the same current for the same current I will get higher lambda which is being set up. So, this is just an example I am discussing. Concepts are very general, but I am trying to correlate it with that example. Now, suppose I am somewhere here. Okay, let us say I am somewhere here, and so what happens here? Lambda remaining constant. Okay, our force FLD equation was minus of W FLD with respect to dx. That means automatically it means lambda is constant. So, lambda is constant in the here. So, I have to put a straight line like this. Okay. So, lambda is constant. That means I am on this red dark straight line, and now I think we discussed this earlier, but let me again do this. Lambda I, this is E is equal to d lambda by dt, power is E I d lambda. So, incremental change, and provided there is no mechanical movement which is happening here, E I dt will be equal to, what am I doing? I have E also and I have d lambda by dt also. E I dt will be equal to I times of, when there is no mechanical work being done, the system being holding on to a fixed configuration, configuration. So, if I am here I, then this is the lambda, and then I do a d lambda. So, this small area is the incremental step here. So, therefore, when I start from here and let us say reach here, then I am going to add this, and so this becomes my this becomes my WFLD. So this becomes my WFLD and the magnetic field energy, that BH curve area above it up to my final point. This area above the BH curve up to my final point looking into this rectangle is the stored magnetic field energy that I will get. Now, how I have defined co-energy? Now, you can, from this picture you can see very clearly what I mean by co-energy. This picture makes it very clear. W dash of FLD, the W dash of FLD is lambda times of I minus WFLD. So, what is lambda times of I? The lambda times of I is this, rectangle area, complete area, minus this area which is the WFLD area. This is subtracted from this whole of the rectangle area. So, what is left? This is left, and this shaded area, represents what? This represents W dash or the energy. So, that rectangle is made up of energy plus co-energy is equal to rectangle lambda times of I. Now, is equal to the rectangle lambda times of I. Now, in this case lambda remaining constant, okay, the lambda remaining constant, initially what was the energy? This is the initial energy, and it moved a bit inside or whatever, that plunger pulled it or whatever. So, the new BH curve, lambda I curve turned out to be this. So, therefore, the new energy is only this much. So, the initial minus the final, initial minus the final is this, initial minus final is this shaded strip, is going to be what? Minus of WFLD. Why minus of WFLD? Because WFLD is sorry, DWF minus of delta WFLD. Why minus? Because WDFLD is what? Final minus the initial, but this area which we have shown here is actually initial minus the final. Because it is initial minus the final, it is negation of the change. So, therefore, it is minus of W of FLD, and so to say this is my original, and this is after dx. This is the way we, and this rate of change with respect to delta x, limit delta x tending to 0, but the lambda has been kept constant, has been defined as f of FLD in our magnetic concept, magnetic partial derivative with respect to magnetic field energy concept. Now, look at it from the co-energy perspective. In the co-energy perspective, so again let me draw. Oops, I am sorry. 1, 2, A, B, lambda and I. This is the BH curve or whatever, and Now, what are we going to do to calculate FLD dash with respect to this is what is going to be my force. So, what is here kept constant? It is I which is kept constant. So, to keep I constant I should look at, I am sorry, to keep I constant I should look at this vertical line. Here is the I which is going to be kept constant, and there is this small movement of dx. So, this is the initial co-energy, this is the initial co-energy, this is the final co-energy, this is the final co-energy, this is the initial co-energy. Final co-energy minus initial co-energy will be the area enclosed in this. So, therefore, area enclosed is this comes with, this is final minus initial. So, it is W delta FLD dash, and this with respect to dx in the limit delta x tending to 0 will become equal to FLD. So, now I think the geometrically how the both things are clear to you in the, when you looked at rate of change of magnetic field energy with respect to x, partial derivative keeping lambda as constant, there was a minus sign. Why that happened, that is clear from this picture. And when you looked at rate of change of co-energy, that for the same movement this reduced, but this increased, and therefore, while the first one had a minus sign coming with it, the second one did not have the minus sign coming out of it. So, now let us just close again that previous example that we were doing, where we calculated that the WFLD will be half of, once the x is fixed, L is only a function of x, and in that plunger setup kind of example, mu r was infinity. So, L was only a function of x and is not really a function of I. So, L is function of x. So, the magnetic field energy and the co-energy are going to be one and the same, and WFL dash we had already derived, it is equal to half of lambda x of I square, and when you substitute for I, sorry, for L of x. Now, earlier we did what we had done, for I we had written as lambda by L, and then I square became lambda square by L square. So, that became equal to lambda by L, L is a function of this. Then I took partial derivative, then this became minus of 1 by L square into L by x, and so on. You remember that. All that is not required now. Now, because I am going to take partial derivative, and see, if the BH curve is a straight line, incidentally, means if the lambda is just a straight line as in this example, because only reluctance is coming out of the air gap, then this rectangle, half of this area is field, half of this area is this thing, and WFLD is equal to WFLD dash, WFLD is equal to WFLD dash, this is equal to half of Li square is equal to half of lambda square by L. So, I am using now this WF dash f of L of d is given by this, because my state variable is now, when dealing with co-energy, the state variable is current, and I am going to take the rate of change of this with equal to this. So, half of I square del L with respect to del x, and what was my what was my this thing. So, equation I have already did I, where is my let me pick up that equation, give me just a minute. So, remember, okay, while I am here, just remember this one FLD, when earlier we had derived it as minus of n square mu 0 L by 4 g I square, just remember that, unit being newtons. And now because it is a linear system, both are one and the same. So, let me copy this here and bring it down somewhere here. Let me paste it here. Remember, because only air gap is there, mu r is infinity. So, this is a linear system. So, energy and co-energy are one and the same. So, this is WFL dash also, and now FLD is WFLD dash with respect to del x, which is same as I remaining constant, half of n square mu 0 L d by 2 g into 1 partial derivative with x will be 0 and minus of x by d partial derivative with x will be minus 1 by d. So, therefore, minus of n square mu 0 L by 4 g newtons. So, now it is clear to you, minus is automatically coming here. So, you do not need another minus sitting here. You compare this equation with, let us copy paste this, it is fun to see everything coming out properly. Let us copy this thing, copy from here. Let me paste this here, and can you see now, term by term these two are matching. So, whether I calculate it from an energy principle or co-energy principle, the force will always come out to be same. It should, otherwise something I am doing wrong. Which one I use? Many times, as we will see further, co-energy concept seems to be more convenient to use. So, we will use, because we are controlling currents, no, current we want to be state variable, lambda rather being a state variable. Instead of that, we are more happy to use current as a state variable. So, this is why we like to work in terms of co-energy. So, I think these two lectures sort of connect your concepts of energy, co-energy and the field created force which is happening due to change in the electromagnetic field or magnetic field which is there, is connected. I think we will stop here. I will take few more examples and continue in the next class. Thank you.